In this lesson, I'd like to cover the topic of asteroids, comets, meteors, and the main features of the sun. It's quite a bit to get through, so let's get going. Start off with asteroids. Asteroids you've probably heard of before. You've probably even seen pictures. I'll show you a couple in a second here. You got a huge chunk of rock, and it's orbiting the sun. Just to remind you, this is exactly where we would find these asteroids. Recall that you've been asked to memorize the order of the 4 inner planets, the asteroid belt, the 4 outer planets, Pluto, and then the Oort cloud. And here we see there's the Kuiper belt or the asteroid belt right there in the middle. So it's very, very close because it's not as far as Jupiter is. It's in between here. And if we look at this picture from that first note as well, we can see roughly the distance that the asteroid belt kind of takes up compared to where our inner planets are and where Jupiter's orbit begins. So it's a lot closer to the rocky planets than it is to the gas giants. So we can imagine it would be somewhere in this particular section right here, closer to Mars than it is to Jupiter. Some of these asteroids are quite small, and some of them can be up to 1,000 kilometers across. Recently, NASA scientists were actually able to land a probe and collect samples from an asteroid. And I'd like to show you a bit of that clip right now.
Tonight here, the first images after that history made in space. NASA pulling off an astonishing feat. For the first time ever, landing a spacecraft on a hurtling asteroid 200 million miles away. That asteroid going 60,000 miles an hour. But they stuck the landing, all to retrieve a sample.
We're going in. We're going in.
The NASA team in Denver celebrating.
Touchdown declared.
The spacecraft OSIRIS-REx landing on the asteroid Bennu. It had to carefully and precisely descend to a spot no larger than a couple of parking spots. And tonight, the first images coming in. NASA releasing video of OSIRIS-REx touching down and collecting those samples. The mission lasting all of 6 seconds. And if all goes well, it'll take about 3 years to bring those samples back.
NASA released an animation that showed how they were actually collecting those samples. And this little weird foot that landed for 6 seconds, if you look to the inside of that foot, you can see that it actually is able to suck up, like a little vacuum, suck up little loose pieces of rock and dust called a regolith, puts it into its little chambers, and then it's able to take off from the surface. And not only is there an analyzer on board where it's actually able to check out some of those samples, but they can actually carry the samples themselves back to Earth, and it'll take about 3 years to accomplish that. Sometimes asteroids can actually fall out of the Kuiper belt or the asteroid belt. And if that happens, they start heading towards the sun because the sun is pulling it with its gravity. So that's the deal with asteroids. So what is a comet, you might ask? Well, before we hit comets out in the Oort cloud, and again, here's where you would find the Oort cloud. So again, the sun, the 4 inner planets, asteroid, 4 gas giants, Pluto, and a bunch of other little dwarf planets that are out there. And then the Oort cloud. The Oort cloud is special because it is the source of where we think the comets are coming from. So as I mentioned, Pluto is out towards that area as well, and it's considered a minor or a dwarf planet. That's why it used to be included in our list of planets, but we've removed it for a few reasons. One being that it is quite small, and the second, it's actually smaller than our moon. And then secondly, not just because it's a small planet, but also because it doesn't follow the same type of orbit around the Earth. And there is a video on Pluto that I'd encourage you to go and watch on our D2L classroom. Right? It's presumably made of large chunks of rock and ice. We recently had a flyby of Pluto that gave us excellent pictures. We've seen it better this past couple of years than we've ever seen it before. So pretty exciting research being done on Pluto right now. But beyond Pluto, if you go past the 9th planet, then there's more chunks, and these are the comets that are in the Oort cloud. A comet is a celestial object. It's made of ice and rock, or you could say it's ice and dust, because once it begins to melt, it leaves behind dust and rock trails. It's kind of like a giant, dirty snowball, if you can imagine that. Remember that as soon as you hit the asteroid belt, you have hit the snow line. So any water beyond the asteroid belt should be solid water. And that's why we would call that ice rather than having liquid water that far away from the sun's heat. Okay? So gravitational forces sometimes disrupt its orbit. That's a fancy way of saying it falls out of orbit and it starts to head towards the sun. Then what ends up happening is as it heads towards the sun, and you can see it in this diagram down here, as it begins to head towards the sun actually heats up the comet and it leaves behind two specific tails. One of those tails, which is represented here in purple, is the dust or the little chunks of rock it leaves behind. And the other is all the gases that come off, things like water vapor and other gases that may have been trapped, start to escape. Notice what happens that as the comet heads towards the sun, the tails get pushed in different directions here. And in fact, when the comet comes around and begins to leave the sun, so it whips around with the sun's gravity, you can actually see that the gas tail is actually in front of where it's going and the dust tail is pushed to the side. And the reason for that is one of the features of the sun is that it sends out something called a solar wind. And it actually literally is pushing out in all directions, this solar wind. And as the comet is heading towards the sun pushes the comet tails away, and as it comes around here, it's still pushing away. The gas tail is much lighter, so it will literally always be exactly facing away from the sun. Notice in every case, that's what's happening with this red gas tail. The rock or dust tail will also try to push away, but it's made of heavier material, so it doesn't quite push away quite as much as the gas tail does. And that's why it ends up being sort of at this weird angle. Rather than traveling behind the comet like you'd expect the way this picture is over here, they actually both end up traveling, most of the gas tail, traveling in front of the comet. I'd like to show you a quick video of what comets actually look like, provided by NASA Imaging.
On December 15, 2011, NASA's Solar Dynamics Observatory captured this footage of Comet Lovejoy approaching the Sun. An hour later, it watched as Lovejoy came around the far side of the Sun and began its long trip back to the outer reaches of the solar system. Other NASA spacecraft, such as SOHO and Stereo, also saw Lovejoy's close encounter. Lovejoy marked one of the few times that orbiting telescopes have been able to watch a so-called sun-grazing comet survive its trip around the Sun. Most are not so lucky. Besides being interesting to watch, the images and data collected by NASA's solar observing fleet can also help scientists learn more about the Sun itself. One of the biggest features that comets help reveal is the Sun's magnetic field. Since magnetic fields are invisible, we can only observe them indirectly, like using iron filings over a bar magnet. On the Sun, astronomers can look at where hot plasma in the Sun's atmosphere is trapped by fields to see their complicated loop structure. But farther away from the Sun, where the plasma is less dense, this approach doesn't work. Comet tails, with their ionized gases, are affected by magnetic fields, and so they can act as brief tracers. On April 20th, 2007, Comet Encke had its tail stripped off abruptly by a coronal mass ejection that carried a strong parcel of magnetic field through the solar system. Even closer to the Sun, astronomers were astounded to see Comet Lovejoy's tail glowing in extreme ultraviolet light as it approached the Sun. They now think the glow is caused by energetic electrons in the Sun's corona interacting with oxygen from the comet. The glowing tail followed and illuminated some of the Sun's magnetic field lines. Careful analysis of the frames allows scientists to reconstruct where the field lines were, and even, to some degree, how strong they were. These comet tracers also illuminate small structures in the Sun's upper atmosphere, where they are usually too faint to be visible. Continued observation of sun-grazing comets will also help astronomers understand how hot material in the Sun's corona cools, and where that energy goes. Finally, long-term observations of sun-grazing comets will help us learn more about the solar wind. Some of the particles in the corona are traveling fast enough to escape and travel through the solar system. They begin moving at roughly 250,000 miles an hour, but start accelerating when they reach around 1 million miles from the Sun's surface. By 5 million miles out, they are traveling at up to 1 million miles per hour. The exact mechanism for this acceleration is not known. Comet tails that are blown off by the Sun travel with the solar wind and can act like a dye tracer in a river. Because they are made of different materials than the usual solar wind, they are distinct and easy to pick out, so they can show exactly how the acceleration unfolds. Because we are in a period of high sun-grazing comet activity, scientists can expect many more chances to watch these natural research satellites in the coming years. In fact, another large comet is expected to have a close solar pass on November 28, 2013. This comet is roughly the size of Hale-Bopp, so it should give quite a show. It will also undoubtedly be a treasure trove of information for scientists, and who knows what new solar secret it might unlock.
When that tail passes through and as the chunks are melting, it'll leave behind that gas and that dust as it travels around, and you can actually see it because the sun's light will then shine off of the tails that are left behind. As it's passing, you can see it lit up for a few days. Our next celestial object is a meteor. Now, a meteor will go through the sky. Literally, it is actually in our atmosphere in a few seconds worth, and it looks like what we call a shooting star. Now, of course, it's not actually a star. Instead, what it is small pieces of rock that are floating around in space, and they don't necessarily have any kind of defined orbit. They're not going around the Earth. They're not going around the sun. They're just sort of free-floating there, as far as we can tell. And they're usually leftover pieces from a comet's tail. So if we have this red dot representing the Earth and this blue dot here representing the sun, as the Earth revolves counterclockwise around the sun, it might encounter, here's a comet's path that left behind a tail, it might encounter a bunch of different chunks of rock that were left behind after the comet went past. And when we go into that particular area where there is that dust that's there, we are moving so stinking fast, 103,000 kilometers per hour, that we actually smash into those meteors. We strike them. And because we hit them so quickly, there's a ton of friction and they burn up in our atmosphere. So if it's a chunk of rock that's floating around in space, we would call it a meteoroid. If it's in the Earth's atmosphere where it's burning and you can see it on fire, and that would be the shooting star, we actually call it, in that particular location, we say meteor. Usually they burn up here. You really don't have a whole lot of leftover material. The entire thing gets consumed and burnt up by the friction. But every now and then, a small chunk of the meteoroid manages to make it to the Earth. So if we can actually find the rock on Earth, we call it a meteorite. Now, a meteorite could actually be from one meteor, but can be found in a whole bunch of locations because as it's coming into the Earth's atmosphere as a meteoroid, it breaks up. So you can have one meteorite, but have all broken chunks in different locations on the Earth, but they would still consider it one meteorite. Let's quickly take a look at this video that helps to give you a distinction between meteor, meteoroid, and meteorite.
In 1969, a celestial light show burst through the sky over Chihuahua, Mexico. These lights in the sky are called meteors. Or is it meteorites? Maybe meteoroids? Are those all different things? And if they are, what is the difference? Actually, they are all different, but they're pretty closely related. The streaks of light are in fact meteors. But the small rocky bodies that cause the lights, those are meteoroids. And when a piece of a meteoroid survives the trip and hits the ground, that object is called a meteorite. So let's talk about our Mexican light show. It actually started out as a single object about the size of a car flying through space. That object was a meteoroid, a body orbiting the sun that's smaller than an asteroid or comet. In February 1969, that meteoroid hit Earth's atmosphere and it hit it fast. Meteoroids fall at a minimum speed of 25,000 miles per hour. At that speed, the friction from the air began to heat up the object. In fact, it made it so hot that it began to burn brightly across the sky as a meteor. This particular meteoroid didn't just burn, it exploded into pieces. Now, most meteoroids burn up entirely as meteors, and some of these pieces did just that. But a few made their way through the atmosphere to hit the ground. Those remnants are known today as the Allende meteorite. Yeah, even though there are lots of stones, they're all considered part of the same meteorite. All in all, about 2 tons of this meteorite was recovered. So where do meteoroids like this come from? Well, almost all of them are actually fragments of asteroids, the larger rocky bodies that orbit the sun in a big belt between Mars and Jupiter. A few, though, are actually moon rocks, and some even come from Mars. So if you ever see one of these interplanetary travelers lighting up the night sky, now you'll know that you're seeing a meteor caused by a burning meteoroid. And if you're very lucky, you might even find a meteorite when it hits the ground.
Finally, let's take a look at some of the prominent features of the sun, including the layers of the sun, things like solar flares, prominences, and other parts of the sun. Now, what you need to know, and we will talk more about this when we talk about the life cycle of stars, but the sun is considered a medium mass yellow star. It's halfway through its life cycle, as what they believe, and we'll talk about the Hertzsprung-Russell diagram and why they think that. And the composition, as far as we can tell, is mostly hydrogen, about 3/4 hydrogen, and about 25% helium. And then the rest is made up of some heavier elements, including carbon, oxygen, and even iron. Now, only larger mass stars like the sun can actually have heavier elements like this. And again, we'll talk about that in a different lesson. But the basic idea is that a star would start with hydrogen, and it would begin to fuse the hydrogen atoms together and eventually make helium, and then helium can then be fused together to make these heavier elements. But that all depends on how hot the star is, how large the star is, and what kind of pressure and fusion is going on inside the core. So let's get into the details then of the different layers. Now, the sun actually has 6 different layers. Inside the core, you have an extremely high temperature and pressure, very, very, very high. And this is the site of nuclear fusion. Like I said, hydrogen gets converted into or squished together, fused together to become helium, and then helium can then go on to fuse together to become other types of heavier elements. And that gets built up in the sun's core. Okay? During that process, there's a giant amount of energy that is released, and that's partially what's going to cause our sun to swell. And you'll see that the heat moves from that core, and it begins to move up to the surface where it's released. And that part there is called the radiative zone. You can see it down in this picture down here. It is the thickest layer, as far as we can tell. It's about 3/4 of the way up to the surface, and it has extremely dense plasma. What's plasma, you might ask? Well, if you remember back from the chemistry unit, we talked about the different phases of matter. You have your solid, which has the matter with smaller amounts of energy, not moving very quickly and quite closely packed together. And then you've got a liquid where they're a little bit moving a little bit more, and you've got the expansion of the material. Then you get a gas, which is even farther apart because it's got way more energy. Well, plasma is the next step above a gas. It's these charged particles that are very, very active and moving. And so they're quite spread apart, and they are ionized. And that's very, very dense plasma in the radiative zone. What ends up happening then is light and other types of radiation are continuously absorbed, which means they get sucked into the molecules that are there, and then they get re-emitted, which means released again. So you have the light being sucked in and let go many, many, many times in all different directions. And because it's this random absorb and re-emit, they think it actually takes 100,000 years for the light to travel from the radiative zone out to the outside where it could actually be released and come towards Earth. Above the radiative zone, we have the convective zone. This is where you have kind of like a heating and a cooling effect that begins to happen with the top layer, basically, of the radiative zone. So what will actually happen is the really hot plasma will expand and it will rise to the surface due to density, and then it will cool and let go of some of its heat. And then because it's cooler, the particles will come closer together, get more dense, and fall back down. And that'll just keep happening. It'll heat up, cool down, heat up, cool down, heat up, cool down. And you just constantly have this churning of this particular layer, right? Beyond the radiative zone, beyond the area where we have this convection, that's the circulation of the plasma, then you've got the photosphere and the chromosphere. Now, the photosphere is basically the yellow part of the sun, and it's actually way cooler than any other part. It's only, I say only like as if it's cool, but it's 5,500 degrees rather than 15 million degrees. So it is significantly cooler than both the radiative zone and the core itself, that where all the fusion is happening. So coolest part of the sun, still ridiculously hot. And this is the part that we can see from Earth. The chromosphere, which is the red kind of section there, chromo meaning color, this red section can actually only be seen during a solar eclipse. And if you look at the picture on the side here, you can sort of see there's a bit of an edge of red. And that'll only happen when this dark section right here is, you can actually see the craters on there. This is the moon. When the moon perfectly lines up from our vantage point on Earth and completely blocks the sun in the middle of the day, for a moment in time, a very short period of time, you will be able to see the chromosphere. You can only see it, though, when the brighter part of the sun is hidden. And you can only really get a good glimpse of all these shiny bits coming out here. That's called the corona, which means crown. And this outer bit here is very beautiful and very visible, again, during a solar eclipse. When you can block out the bright disk of the sun, all of a sudden you realize that the chromosphere and the corona are there. Otherwise, the sun itself is too bright to look at. Even in this stage here, mostly covered in a total solar eclipse, it still is enough light energy to permanently blind you. So you have to have either special glasses that allow you to look at very bright things, or you have to do a fancy version of looking at it through something like a colander and whatnot. Hopefully, you were around when we had the solar eclipse a few years ago, visible here from our location. So let's zoom in now on the surface features of the sun. So looking at the surface, we can see things called sunspots. Again, looking at it through special lenses. Obviously, we can't see this with the naked eye because we would burn our retinas. But you see these darker red sections, and then you have the more orangey, yellowy kind of sections. These darker sections are thought to be cool areas. Those are called sunspots, and this is the part that's cooling and about to fall, the part of the radiative zone that's about to fall down and then get heated and come back up again. So basically, you're looking at the sun boiling is really what it is. It has a very, very strong magnetic field, and what that does is slow down the convection. So how much is rising and falling in the radiative zone is sort of controlled by this magnetic field. And it prevents the plasma from mixing, and it cools. So it gets from somewhere between 6,000 to 4,000 degrees. Now, there is a maximum number of sunspots that happens in a cycle of every 11 years. Notice here, I don't know if you've seen it already, but there's a little tiny Earth to show you the vast difference in size between the sun itself and the Earth itself. Another major feature of the sun is called a prominence. A prominence is this big curved sucker that pops out right here. The reason it pops out and comes back in again is because there is a huge magnetic field. If you've had a chance to play with magnets and you were able to take little pieces and little chunks of iron called iron filings and dump it on top of a magnet, you would actually see those iron filings line up exactly like I've drawn here on the left-hand side. They would line up in these rings because that's where the magnetic field is, and they would all line up with the magnetic field. So what you're seeing in the prominence over here on the right is evidence of the magnetic field. It loops out and it comes back in exactly where the magnetic field is. The next feature of the sun would be solar flares. These are huge big explosions that happen on the surface of the sun, and when they explode out, some of the material, rather than being caught in a prominence, will actually escape the surface of the sun, and it'll be thrown towards all parts of the solar system. When they come in, they actually come in our direction. It takes about 3 days for it to get to us. It bounces off the Earth's magnetic field. So you can see here's a solar wind pushing the solar flares towards Earth, but because Earth itself is a giant magnet, the actual solar flares will bounce off, and most of the particles will never reach Earth, all because of our wonderful iron core that makes the Earth this huge magnet. What it does do, aside from messing with satellites and actually electrical transmission lines, is when it bounces off the actual magnetosphere, you see these beautiful, colorful things in the sky, changing and beautiful, called the auroras. In the northern hemisphere, casually we call it the Northern Lights, but the real name of it is Aurora Borealis. You can get the same effect in the southern hemisphere, and you would call that Aurora Australis. Let me show you a quick little video that demonstrates what the auroras look like.
Here's a story. Now, imagine there's an invisible force field around our planet. And now imagine that for billions of years, that force field's been protecting us from a beam of supercharged plasma that would otherwise wipe out life on Earth as we know it. Now, you might think this is some kind of science fiction story, but it's all true. And it's what gives us this, the aurora. So the aurora is one of mankind's oldest mysteries. We've come up with some crazy theories of how to explain it along the way. Well, take Aristotle. He thought the aurora was the sky vomiting little bits of flames. But it wasn't until the 1600s that we figured out two key things that helped us explain the aurora. One, the Earth is really just one big magnet. And second, it turns out that the sun gives off a lot more than just light. Long before any sunlight hits Earth, it's born at the edge of the sun. And the edge of the sun, the corona, is a busy, beautiful place, full of churning whirlpools of plasma and huge magnetic arcs. All that action is constantly releasing waves of energized particles, creating what we call the solar wind. Now, a few days after leaving the sun, traveling at a whopping 400 kilometers per second, that blast of charged particles reaches Earth. But luckily, we've got a secret weapon on our side, Earth's swirling molten core. Our core is the key to life on Earth. It creates a magnetic force field around us that deflects the solar wind up and away, making life down here much more enjoyable. Now, because of that magnetic field, we have nice things like an atmosphere, and we're much less burned to a crisp thanks to wave after wave of planet-sterilizing radiation. But despite all that, a tiny bit of that solar wind does hop on the magnetic field and ride it up or down to the Earth's poles. And that's where we get the auroras. When those energized particles smash into gases way up high in our atmosphere, they excite them, which means the gas atoms grab onto a bit of energy. But they don't stay excited for long. They give off that stored energy in a bright burst of light. Different atoms in our atmosphere each give off different colors. Excited oxygen is what gives off that familiar green and red that most of us think of when we hear aurora. But there's also nitrogen up there, and it can give off a really cool mix of red and blue light that makes the sky glow this incredible purplish pink. Now, we can only see this happening at night, but it's happening 24 hours a day of every year. It's also happening on Saturn and Jupiter. Sometimes the sun takes that wind and turns it up to 11, and that can be a very dangerous sight to behold. Now, extreme solar storms called coronal mass ejections can erupt into space almost without warning, unleashing huge waves of charged particles. And if they happen to be pointed at Earth, then look out. Now, these storms are incredibly powerful. Astronauts that are working outside of the Earth's magnetic field say that if you close your eyes during one of these solar storms, you'll see bright flashes of light from the charged particles reacting with the fluid inside your eye. And in 1859, a storm so powerful hit Earth that it powered a telegram from Boston to Portland, Maine, with the equipment unplugged. When those rare, violent storms hit Earth's magnetic field and ride up to the polar atmosphere, we're treated to an aurora show like no other. Now, these images are more than just works of art. They let scientists study how solar storms affect life here on Earth, like our electronics, our communications. Some of the best views of Earth's auroras have been captured from the International Space Station. The space station passes near the north and south poles of our planet about once every 90 minutes. So if they pass by the poles when it's dark, the auroras are close enough to reach out and touch, although I wouldn't recommend that.
And that, my friends, is the end of this lesson. Please make sure you head over to our D2L classroom and take a look at the YouTube link for the sun. You just have to scroll down a fair bit and you'll find it right here under Asteroids, Comets, Meteors, and the Sun. There's also a link here to the OSIRIS mission, which has all the information about when that little spacecraft actually touched down on the asteroid. So go ahead, get that done, do your homework that's listed in your booklet, and everything will be grand.